All right, so if you're watching this video, I'm hoping that you're ready to practice several things in Unit 2, including Lewis structures, writing formulas, chemical reactions, balancing those reactions. So what I'm going to suggest to you is that you have paper, pencil, perhaps a calculator, a periodic table, and a table of electronegativity, and that you pause the video several times so that you can work out some of the problems. All right, so let's go ahead and get started. All right, so that's what we're going to be doing this evening, all those things that I just mentioned. And so here's your first one. Can you draw this structure, figure out its shape and its polarity? So go ahead, pause the video, and let's see what you can do. All right, so obviously the first thing that you probably had to do is to figure out what the formula for this molecule is. And then you're going to have to go ahead and figure out the valence electrons. So of course, carbon has 4, hydrogen each has 1, so that will be 2 from hydrogen. Oxygen has 6. And so that's a total of 12 valence electrons. Now I'm going to figure out, okay, what am I going to put in the middle here? Again, generally it's the first atom and the one that we have fewer of. So I'm going to put carbon in the middle. Then on each side of carbon, and I just decided to go above and below, I'm going to put a hydrogen. I could have put those somewhere else. And over here, I'm going to put an oxygen because it isn't exactly symmetrical. And then as I put in those bonds between carbon and hydrogen, carbon and oxygen, I'm now going to go ahead and take off those 6 valence electrons. And notice that I have 6 more to go. And so where am I going to put them? I'm going to put them right on this oxygen. And now I'm going to check to see if everybody has an octet. Well, and of course, hydrogens only need that duet. So I'm going to say, yep, they got it. Oh dear, this carbon doesn't. It only thinks it has 6 valence electrons. So that's where I'm going to go ahead and I'm going to turn one of these lone pairs into a double bond. And so that lone pair is no longer going to be there. It is now a double bond. And so there we go. So there is our structure, of course. And so now we're going to go ahead and get rid of that. And so what shape is this structure? Well, we've got our central atom. We've got 3 things bonded to it, no lone pairs. So it's going to be trigonal planar. And so the next thing we're going to be taking a look at is how are they sharing their electrons? Does it contain polar bonds? Well, the bonds between the carbon and the hydrogen are going to be non-polar. We're looking at hydrogen with an electronegativity of 2.1, carbon with an electronegativity of 2.5. So that is a difference less than 0.5. But then oxygen and carbon, oxygen comes in with an electronegativity of 3.5. So that is a significant difference. And so this does have polar bonds. And so, yes, it does have polar bonds, as you can see. Here's a picture of our molecule. And so because this oxygen is way down here, pulling on those electrons more, making that end of our molecule a little bit negative, leaving this end a little bit positive, it is going to be a polar molecule. So how did you do figuring all that out? All right, here's our next thing. Again, that electronegativity difference is greater than 0.5. So we do have a polar molecule. Here's just a little picture to represent a polar bond. Remember, the more electronegative atom pulls on the electrons more, so those electrons spend more time around that atom. So in the last case, those electrons would have spent more time around that oxygen. All right. Okay, let's take a look at this reaction. What'd you say? What would you say? This was from your experiment number 5. This was the first reaction. Hopefully you're saying that it was not balanced. It is a decomposition reaction. So to balance it, you have to put this coefficient of 5 right there. How about this one? I see one product, multiple reactants. The reactants are all elements. The product is a compound. So that is going to be a synthesis reaction, and it is not balanced. So how would you balance it? What coefficients would you add? Hopefully you're thinking you would add a 3 there and a 2 in front of NH3, nitrogen trihydride. Here's another one for you. Hopefully you were thinking combustion. You're exactly right. Here's your fuel, your oxygen. Your products are always CO2 and H2O. Is this one balanced? No, it's not. So how would you balance that? Yes, you'd have to add those coefficients of 2 in front of oxygen and water. All right, how about this reaction here? So I'm going to have to take a look at it. I'm noticing my reactants. I got a compound, I got an element. My products, I have a different compound and a different element. So hopefully you were thinking single replacement reaction, and you are exactly right. It also looks balanced as I've got it written here. I'm checking out 2 hydrogens, or 4 hydrogens, excuse me. 4 hydrogens, 2 here, 2 there, 2 oxygens, 2 oxygens, 2 lithiums, 2 lithiums, so balanced. How about this reaction right here? What would you say? Hopefully you said double replacement. It is not balanced. It does not look balanced to me, because right here I see 2 Ks, and over here I would need 2 Ks. I also see 2 NO3s. Notice that that polyatomic ion nitrate stays together, so I would need 2 right there. So I would simply just add that coefficient, and then it looks balanced. 1 Ba, 1 CO3, there we go. All right, and so you may want to, I apologize, I've got a typo here, practice balancing them right online. This is a really great website where you can practice balancing those equations. I hope this helps you as you're moving forward.